Today we look into another yet another type of non-deterministic automata, finite automata. So we have already seen non-deterministic finite automata in the previous lecture, and that was already a generalization of deterministic finite automata, DFA, right? So this is a further generalization of the NFA that we studied in the previous lecture. So here the new thing is that you can have transitions labeled by this empty string. Okay, so this thing. So you can have transitions like this. So here is a complete automata. You can have transitions on symbols from your input alphabet, and you also have transitions like this. Now, what does this transition mean? See, in the normal NFA, the normal NFA means without this epsilon transition. How did we accept string? So we start with this starting state, and we process a string. Say our string is this symbol A1 up to AN, and we process this string, and that amounts to following a path, right? And there can be many paths, right? For NFA, there can be many paths, and if at least one of that path leads to a final state, okay. So if there exists any one path such that you start with this starting state and you process this thing and you go to this final state, if there is at least one such path, then we accept, right? So here, if we consider similar paths from, say, a starting state, now this arrows corresponds to some edge in our graph, right? So here this transition means you are jumping from states to state. So the only difference is that here all these labels were just symbols, right? They were just elements of the sigma. So now these labels can be either symbol or this empty string epsilon, right? And the acceptance criteria is same. If you just consider this modification. So what is the acceptance criteria? That there is at least one path, right? Again, there can be multiple paths because it's a generalization of NFA, and still you can have some state from which you can have multiple transitions on the same symbol. So that is allowed. But if there exists at least one path such that the symbols, if you put together all these symbols and these epsilons, if you concatenate all those things, suppose you get this W, and this path is such that it starts from the starting state and finishes at one of the final state. So then you say that this W is accepted. Okay. So the only difference here is that here the AIs are either symbol or this epsilon, empty string, right? So that is the only difference. Otherwise, the acceptance criteria sounds almost same, right? Now we need to formalize this idea. Again, we need to define the transition function. We need to define the extended transition function that we normally denote by hat. Okay, delta hat. So somehow we have to define that, and somehow we need to capture this notion using that hat function into some equation, proper equation, right? And that you will see will look quite messy. It's much cleaner this way, and the equations will look kind of very complicated, but essentially it is saying just this simple thing. Okay, so just keep this in mind, and then the equations will be quite clear to you. So as I was saying, how do you accept a string? So you accept if there is a path from this starting state. So in this example, our starting state is just q0, right? And from q0, if you can reach this q2 on some by processing some string, so then you accept that string. So now take for example this string, okay, just 1 1. Now again the difference here is that these AIs can either be symbol or epsilon. Since we are also considering epsilon, now breaking down this 1 1, so this breakup can happen in infinitely many ways, right? So if we do not allow this epsilon, then this 1 1 can be only broken down into 1 and 1, right? So there will be just a1 here and just this a2 here, nothing. So this is the only breakup into symbols. But now since we are also allowing this epsilon, we can break it down into 1 and 1, epsilon 1 1 1 1 epsilon 1 epsilon epsilon. So there can be any number of intermediate epsilons, right? You can have in fact array, so a series of epsilon, whatever number you like, and then you can have one, then again a series of epsilon, doesn't matter. You can have all this epsilon, then again this one, so you have one here, and then again some epsilon, doesn't matter how many you want. Now considering all such breakups, this infinitely many breakups, if at least one of them give you a accepting path, that means a path from q0 to q2, so then you accept. And here you see that this is a accepting path. So how do you accept 1 and 1? So again, it's easy. If you just see it here, you just follow these arrows, right? Starting from here, you follow the arrows to reach q2. So you first take this, so you take epsilon, then you take 1 on this path, again 1 on this path, and then you take this epsilon to reach q2. So epsilon 1 1 epsilon, so that is accepted. But still there will be some string which for which there such path does not exist. For example 1 0, right? So now how can you process the first one of this 1 0? So again you have to first take this epsilon transition and then take this 1, and after that there is no way to process this 0, right? From here there is no outgoing edge with 0, so you cannot even process this 1 0, let alone reaching this q2. So you get stuck and you reject, right? So so you can see that the main feature of this machine is that this automata can change state, right, without reading any input symbol, right? For example, what happens here? It starts with this q0. It starts with this q0, and then even without reading this first one, right? Even without reading this first one, it first changed its state. It hasn't read any symbol yet, but the state has changed, and then it read this, then it read this, again it's here in q1, which is not a final state, and then without reading any final further symbol, it just changes this state to a final state, right? So this is the difference, that it can change state without reading an input symbol, right? And since this is possible, that it's using some time step to change state without processing the input symbol, the input string, so it may happen that it may take more than this this many step, the length of the input string, right? So this is the length of the input string. So both in case of DFA and NFA without epsilon move, it took exactly this many steps, right? It took exactly this many steps to process this thing, but now it can take more than that, because it can just make a epsilon transition, right? So how do we mathematically express its transition function? So that's very simple, because already in NFA, you must remember, if you forgot, you just look into that NFA video once more. So we had this multiple transition on same symbol, right? So from some state, the next state was not just a single next state, but it was a set of next states, right? So here that feature is included. That kind of non-determinism is already inbuilt here, and on top of that you can have this epsilon transition, and you can just say that instead of symbol here I can have a symbol as well as this epsilon, this thing. Okay, so that means for NFA without epsilon transition, we had the state here and some symbol here, and we were getting a set of state here. But now instead of just considering symbol here, you consider symbol plus this empty string. So this is the change that we see for this epsilon NFA. So for normal NFA, it was just sigma here, right? And in both cases, this is a set of state. It's not just a single state, right? So now previously, for NFA without epsilon transition, the non-deterministic behavior came from this sort of transitions, such that you are in some current state and you are processing some symbol, and there are multiple possibilities to switch to. So that was the non-deterministic behavior. So here you can also have this sort of thing with epsilon. On epsilon, it's not that you need to move to some specific state. On epsilon also you can move to many different state, as it is shown here. But you also just take note of the fact that even if you have this, right? So if you have, say, something like A here and say B here, so then this transition is not non-deterministic, right? On A you will move to exactly this thing, on B you will move to exactly this thing. But here, though you have two different labelings, still this is non-deterministic. Why? Because if you are here, you either can choose to read A and then move here, or you can choose to not read the input symbol and move here, right? So for example, from here you may have some transition like this, right? So now if you are here, say in state Q, and suppose the next input symbol is A, so where do you land? So either you can choose to read that input symbol immediately and you go here, or you can choose to just change your state here and then read the input symbol and then go here. So you see that even with this sort of different labeling, you have a non-deterministic behavior. Now one thing I should probably mention, that if you just have a chain, so suppose this is your start state, and suppose you have just this transition, say, and suppose you have this with this and then this, so this is final. So this is, say, your entire automata, right? So what language does it accept? You see that the only thing that it accepts is epsilon A epsilon, which is A itself. So the language accepted by this automata is just this. It contains just this string, which is just this A, right? And you see that here all the steps are deterministic, in a sense that if you are in some state, you know what the current state is. If you are here, you know that it cannot read any input symbol, because the only transition it has is this. So it cannot read any input symbol, and it has to move to this state, and here it has to read A, and it should move to this state, and here it cannot read any symbol, and it must move to this state, and then it accepts this A, and so this is the accepted language. So this in some sense is non-deterministic behavior, and this sort of non-deterministic behavior you get if you have only a chain of epsilons, right? In the automata, it's not just I'm showing one path and there are other paths. No, if there is just this one path with epsilon, 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 then there is no other choice than to just take this path, right? So in that sense, it will be deterministic. The only non-determinism comes when you have a epsilon and something else with that. This can be either some symbol, this can be another epsilon. But if you have epsilon and then some other symbol, so then there is a non-determinism. And obviously there is a non-determinism if you have symbols and you have multiple transitions on the same symbol. So that is already there from the previous notion of NFA. But the only thing is that the machine does not behave non-deterministically just because you have epsilon transition. It behaves non-deterministically because you have a combination of, say, this non-determinism, this sort of thing and this sort of thing, or yeah, you have multiple choices to make on each step. So if that happens, then only you have the non-deterministic behavior. So yeah. So whatever I explained here, it is already there in this picture, and you can see that there are two different paths here. So it's essentially same. So instead of taking this, I am taking this path back. So on processing this A, you see, right? So either you can take this epsilon and then this A and then this A, or you can have, say, this epsilon and this A and then epsilon then this A, right? So all this sort of things can happen. So for this, then the transition table will look like this. So for a non-deterministic automata without epsilon move, so this part was not there, right? So now you have all the input symbols and the epsilon here. And again, you see that we do not need to address partial transition function, because like the NFA, so for example, for this Q0, there are transition for 0, there is transition for epsilon, but there is no transition for 1 or 2, right? So the set of next state on this 1 and 2 is just phi and phi. So that takes care of this not having a transition at all. You do not require partial transition function. Transition function is total. So now the next step is to define this hat, this extended transition function, and the acceptance criteria in terms of that transition, that extended transition function, that hat delta hat. But in order to do that, first we need to define this epsilon closure. Okay, so we will require that. So how do we define this thing? So suppose you are in some state Q, okay, and as I said, you can change state without reading any input symbol, right? So you can change, you can, for example, suppose you are here, and without reading any input symbol, you can change the state to here. Then again, without reading any input symbol, you can change the state to here, right? So the epsilon closure of Q will be all such states, right, to which you can change from, say, Q, so such that Q can change to state P without reading any input symbol, right, in 0, 1 or more steps, right. So the 0 is important because then it says that Q itself will always be in its epsilon closure, right. So if you are in Q1, so in 0 steps you will be in Q1, right. So in one step you can be either in Q2 or Q4 without reading any input symbol, of course, and then you cannot take this because here you need to read one input symbol, but you can take this. So in 2 steps you can be here without reading an input symbol. In 3 steps you will be here without reading an input symbol. So the epsilon closure of Q1 will be this entire thing. So this entire thing will be epsilon closure of Q1, right. So this is the thing, but but suppose we are trying to find out the epsilon closure of Q2. So then you can see that without reading you can only be here with 0 steps, right. We have this 0 many steps here, and with 1 step you can go here, right. This edges are directed, so you cannot go to this direction, right. So epsilon closure of Q2 will be just this and this, okay. So oh sorry, there is another epsilon transition, so I missed that in the previous thing also. No, yeah, so yeah, you have this epsilon transition, so this again, sorry, let me just correct this thing. Yeah, from here you can go to either this or this, so the epsilon closure will be this entire thing. So this is again here. But for say Q4, Q7 and Q6, you see that you cannot move to any other state without reading input symbol. So the epsilon closure will be just this, because we are also considering 0 step. So this, as I said, Q itself will always be in the epsilon closure of Q. So these are just this step. So this corresponds to this 0 steps, right. So this is epsilon closure. Now, what was the idea behind this extended transition function, both for DFA and for NFA, right? So both for DFA and NFA, this actually this informal definition works, right? So that means we are just generalizing this thing into epsilon and NFA. So what was this? So it was the set of states that you can reach by processing this input string W. I'm starting from this state Q, right? You start from Q, you process this input string, and you can take many paths because we are talking about NFA, and DFA is just a special case of NFA. So consider all the paths, and then you will end up in some state, right, at the end of that path. So you take the set of all those states which you can reach from Q after processing the string W. So I should have a W here. Yeah, after processing the string W, right? So what is the signature? So since this is a string, we have sigma star here. So we are starting with some state. So we have a Q here, and then this is a set of states. So we have a subset of Q here, right? Now you can immediately see the most simple case. So if I take epsilon here, right? So that means I'm talking about all the states that you can reach by processing the string epsilon. That means you are not processing any symbol at all. And that was precisely the definition of epsilon closure, right? So you start with Q, you do not process any symbol, so that means you are just processing the empty string, and then the set of state that you can reach is actually this epsilon closure. So that is the very definition of epsilon closure, right? Okay. Now both in DFA and NFA we gave a recursive definition of this thing. So we first defined it for epsilon, and then we defined it for say this WA, right? And recursively, so if we know this for this W, and then we try to express it for WA using the set for W. So we are trying to do the same thing. So suppose these are precisely the states that you can reach after processing W, starting from state Q, right? And this paths, now since we are talking about epsilon NFA, so this paths may consist of epsilon transition. So there can be epsilon transition here, but whatever it is, these are precisely all the states, right? So these are the all possible states that you can reach after processing, say, W. And this is what we want it to be. So this is our delta hat QW, right? So according to this. Now how can we find the states which can reach by processing WA? So we have already processed W. Then we can say read some A, right? And then we will move to some state. So if say this is P, okay, so then this two thing will be what? So this will be delta of PA, right? So there is no hat here, right? Because this is just one transition, right? Since it's just a single step transition, so there is no hat here. So this will be just this delta PA, right? And then we take union of all such things. So we are taking union over all these P's, right? So this is what we get. So this big thing that we get here is this thing. So here in fact it got suppressed. So here we had a hat, perhaps you can see, or I should, yeah. So you see that we have a hat here because this is what we are talking about for this, and then we take all the P, and then we take the single transition, and then this thing. But now these are not the only states that we can reach after processing WA, because now we are free to take paths which consists of only epsilon transition, right? So just pause and think about this thing, that we processed W, then we processed just a single A, and now we can process say 1000 many epsilons if you can find such a path, I mean consisting only of epsilons, right? So what will be these states? So this is precisely the epsilon closure of this state, right? So this is precisely the set of state that you can reach from this state without processing any input symbol. So this is the epsilon closure of this thing. This is the epsilon closure of this thing, right? So this big thing will be the set of states that we can reach after processing WA, right? And how did we do that? So we have this for W, we take this set of states that we can reach for after processing W, and we take each state there, and then we take a single step with symbol A. So then we have again a bunch of state, So since we are taking all p, we will have a bunch of r's here, and for all of those r's, so the r's will be here, right? So this r that I'm talking about is the elements here, here, right? For all those r's, you take the epsilon closure of this r and union of this whole thing, right? So this should be q of wa, right? Now one thing you may ask that, okay, after w we are immediately processing this a, right? So what about this picture, that starting from q we have this say w, and then say without processing this a immediately, so we are again taking this this thing here. Now without processing this, suppose we take a epsilon transition here or multiple epsilon transition here. So we are not considering that possibility here, right? But that possibility is inbuilt, because you see I said this is all the possible states that you can reach from q after processing w. So you see that this w and epsilon together will give you w. So that means whatever this state is, so call this state say q prime, this state, okay? So this q prime will be here, right? So if you have something like this, and then you have some epsilon transition from here to something, so this thing will also be in this set, right? So then if you are considering this set, after this you do not need to consider a separate epsilon transition. You just take this a and then take the epsilon transition, so you take this closure. So this equation holds, right? So then since we have this, it's now easy to express the acceptance criteria, right? So what was acceptance criteria? That whatever state you can reach after processing say string w from this state q0, right? So if you can reach any one of the final state, so then the string is accepted. So that means whatever state you reach, if that contains any state from the final state, so then it is accepted. So again, this line alone is just identical to the NFA, right? So the only difference is that this delta hat is slightly different here, right? Otherwise, you just go back to the NFA video. So this is exactly the equation that we had there, because it's just expressing the fact that at least one of the path leads to a final state, right? And then what is the language accepted by this thing? I mentioned it many times that the language accepted by a automata is just the set of all strings that are accepted. So here we accept a string via this condition. So we take all such strings, and that collection of string, that is a language. So that is the language accepted by this automata, right? So just to make sure that you understood this delta hat, so just check what will be the delta hat of a and 0, right? Again, don't try to chase the equation. The equations will come later. You can figure out those equations if you know what you are trying to do. So what are you trying to do? So starting from state A, you are trying to find all the states which you can reach after processing this 0, right? So if you so that means you can first take some epsilon transitions, and then you can take say a 0, and then again take some epsilon transition. So you can take say this path, this 0, then this epsilon transition, and then this epsilon transition, then this epsilon transition. So all this E, G, H, I, so this will be in your A0, right? And why do we have CD? Because after coming here you can also take this path. So you started from here, you already processed 1 0 along this, and then from here you can go back here and go here, or after coming here you can go to here, so CD will be here, right? Or after coming here you can go to this path, so this will be all these things will be there. So the only things that are left is F and L, right? So now if you process 0 0, what can happen? So after processing just 0, you are in one of this state, right? So from here, how can you process 0? So if you are here, you can process 0. So you can take this and again take this and all this thing. But if you are here, then you can process 0 from here, and you can take this also, since this is epsilon transition. So except this state F, you can reach, okay, so you cannot reach A either. So A is not here, but here also, you see that you will also cover this L here, which is not here. So you can just try to draw some diagrams and try to see, if you are not comfortable with the definitions so far. So this is what delta hat is, right? And this is how we express acceptance in terms of delta. So now we want to just prove one equality identity. So you see, so this again is trying to kind of express the set of next state on input WA using, by breaking it down into W and then A. So we did that thing in this equation, okay, and this is in fact is the definition of delta hat. So this is the formal definition of delta hat, right? This is the formal definition, and we are defining it in terms of delta, right? So if we know what delta is, if we know what epsilon closure is, then this is the definition. Now for that it's fine, but here we cannot take this as a definition because this already has a hat here, so it's not expressed in terms of delta. But this equation is simpler, right? So there we had this two-step kind of thing. So we first take this hat, then delta, and then take epsilon closure. So this epsilon closure is kind of inbuilt into this hat. So this equation looks cleaner, and later we will see that this equation will be used to convert this thing into NFA without epsilon transition. So, but anyway, and this again, if you just think of the picture, so what is this side? So this is the picture that we already saw, right? You take some path on W, then you take the single transition on A, and then you take this epsilon transition. So this is the epsilon closure and everything, right? So this is how we defined this thing. So this is exactly the picture that we saw here when we are trying to derive the definition of delta hat. Now we can also rewrite this thing like this. So we again have this delta hat QW, but then as I said, this epsilon closure is kind of built into this hat, right? Because you see, since we are considering hat of PA, so suppose you have some P here, and then what is hat of PA? So this is the set of state that you can reach by processing A, right? So that means you can take okay, so this is not entirely correct, because you can have a epsilon transition here, and then you can go to some P2 and then can take some A, and you will reach something here, and from here you can have some epsilon. So you can also have this in your you can also have this in your delta P1A, but you see that whatever this thing is, it remains in this big box, right? And if you take the union of all this things, this delta hat of this PA, consider all the P's here. So if you take this thing, so then this is just the same thing, right? So all I'm saying is that this epsilon closure is kind of taken care of because we are using a hat here, and so this picture is slightly wrong, as I said. I mean, you can have also something from here to here and then here to here, but the point is this thing will be included here. So if you are actually going through all the state in this set, if you are going through all the P's here and then taking the union, so then everything is taken care of. So we have just this slightly simpler equation, right? And this is the formal proof. So if you are asked to give a proof, you cannot just draw a picture and say that this is a proof, though that is how we solve it mentally. But you have the equations, you have the definitions of delta. So this by definition is what? So this delta by definition is this thing. So this will give you that equation. So if you are trying to figure it just for one symbol, say, so suppose if we have just one symbol here, so that means this W here is we can take as epsilon, right? So W we can take equal to epsilon. So that means it will be closure of what thing? So closure of R, where this W is just epsilon, right? And if this W is epsilon, then this is epsilon closure of Q, right? So what you will have here is P is coming from epsilon closure of Q, and then R is coming from delta of PA, and then you are taking union over all such R. So that is what we have here. So this is just been replaced by this epsilon closure of P, and this is what you have here. And now you notice that if this P prime is in epsilon closure of if this P is in this delta hat of this QW, then if I take epsilon closure of any such state, so that closure will also be a subset of this set, right? So that means if I take any element from the epsilon closure of P, so that will be a element of this thing itself. So these two together can just be clubbed. So this thing can be clubbed because P prime is in epsilon closure of P means that P is in P prime is in this thing. So there is no reason to just consider a separate p prime. We can just consider all the states here and then take this, and then by definition this will be again, by definition this expression is delta hat of QWA. So we have this proof without the picture, only using the equations, and this will be useful when we try to convert epsilon NFA into a NFA without epsilon transition. So just to summarize what we have, how this extended transition function differ for epsilon NFA and NFA without epsilon transition. So here things are simpler, right? So if you are just calculating the hat for empty string, so it's just the same state that you can reach. But here, since we have epsilon transition, we can reach the epsilon closure from Q, right? So here, this thing, this delta hat of QA was just delta of QA, right? And both will give you some set, but they were equal, right, for NFA. So you can go back to that NFA video. It's in fact simple. Again, what is the definition? The set of states that you can reach from Q after processing A, right? So that's the definition of this. And since there is no epsilon transition, it's just a single step process. So they are same here, right? But here, as we saw that for the single thing, we have epsilon closure here, and then this here, and then this union. So it already looks kind of quite complicated. And then how did we break this up? This comes from the definition. So we are just taking this set and then taking state here, and then taking one step transition from this and taking the union here, right? So again, it was much cleaner, but here we have kind of a union over a two-step thing. So first we take this and then take this and then take the epsilon closure of this thing. So we need to just keep on taking this epsilon closure. But now you see that with this equation that we just proved for epsilon NFA, things look much cleaner, and in fact it's the same expression that we get for NFA without epsilon transition, right? So for epsilon NFA, this equation works with this A being epsilon also, but if you are just considering strings, here you need not consider epsilon. We are just trying to define this thing for all possible strings, and it just suffices to take a symbol here. So yeah, so this equation is identical. And here, why this is true? Because here this hat is actually equal to this, and we have this. So from this and this we get this, right? So but here we had to prove this separately because the earlier part is not exactly same. So what